Categorical features and text as data. 85% of data science projects fail. Why? Well, one very important reason is we don't understand the data. It's not just a preliminary step, it's something we do on an ongoing basis. Projects fail because we don't understand the data we're working with. We must understand the data. And to do so, we go back to the Polya problem-solving process. We've looked at exploratory data analysis, feature engineering, our model building, and analysis interpretation, and that's our goal. But it's not just our goal once. We do this over and over and over. The first repetition, up to analysis and interpretation, is almost always for understanding. The final model is always after one round at least of analysis and interpretation. Why? Well, analysis and interpretation is used to identify issues in the current attempt that can or must be addressed in the next attempt. For example, suppose we have a set of documents, a corpus of documents, and we want to reduce that to a bag of words to the project's vocabulary. But do we have the right vocabulary? That is, more pre-processing in feature engineering as we repeat this cycle of problem solving over and over and over. So let's look at categorical variables. And when we're doing so, correlations can be misleading. Let's look at this example where we have a feature animal and a target tail wagger. We do our usual one-hot encoding. We look at squared correlations of the one-hot encoded features with tail wagger. And these are not well correlated with tail wagger. We might, if this was among a whole bunch of others, we might just throw them out. But the original animal column is a perfect predictor. These three animals, cats, chickens, and dogs, wag their tail. These three do not. Now we can recover this information using mutual information. Here I'm using normalized and adjusted mutual information scores. And notice I get perfect, 100%. But how did I know to use the averaging method of minimum? Well, mutual information of a variable x with a variable y cannot exceed the smaller of the two entropies of x and y respectively. Why? Because the most information you as a variable could share with another variable is the information that you have. Now, the tail wagger, which is our target, has an entropy of log base 2 of 2. There's two labels, yes and no. There are 6 labels for animals, so its entropy is log base 2 of 6. So I want to get the mutual information normalized by the entropy of tail wagger, which is the minimum of the tail wagger and the animal. So text and natural language processing, very important. Text is an important example of categorical features. Generates many of these 85% fail examples, as well as fantastic successes. A typical data set is a corpus of documents. Typical application, natural language processing. Binary classification, spam versus ham, good docs versus junk docs. Next word prediction, phrase completion, and this is kind of also where you would put things like translation from one language to another. And summarization, reducing a large collection of documents down to one or two representative documents. And we often use for this the Natural Language Toolkit. It's a library for human language feature engineering. For example, you can limitize with this NLTK library. That means mapping a word to its root based on its usage. For example, if I limitize cities, I get city. If I limitize churches, I get church. I can use parts of speech, N for nouns, V for verbs, A for adjectives, and R for adverbs. If I limitize better in the sense of he is a better man, that means I'm using better as an adjective, then it limitizes to good. If I limitize bettered as a verb, as in he bettered his opponent, then it's better. If I limitize loving as a verb, I get love. Stemming maps a word to a stem based on structure. For example, the stem of having is have. The stem of flies is FLI. The limitizer is probably what we might have been thinking, limitizing flies to FLY. Tokenization breaks a document into a list of sentences, breaks a document into a list of words, or breaks a sentence into a list of words. For example, I have this string of 4 sentences. I can tokenize the sentences and I get 4 separate sentences. I can word tokenize the entire text, which makes the entire text one long list of things split at the punctuations and spaces. Or I could tokenize a sentence for each sentence in my sentences. There's many others: bigrams, trigrams, punctuation. We'll also be looking at GenSim and Word2Vec, and we'll also be looking at some of the many data sets included in the Natural Language Toolkit. For example, sentiment prediction. Tweets about 4 topics: Apple, Google, Microsoft, Twitter. Each tweet's either positive, negative, neutral, or irrelevant. So here is an example of 4 positive tweets. Some tweets contain URLs and other constructions. The first iteration of polio problem solving is exploratory. So we're going to notice that we have unbalanced data. We have 4 classes, and irrelevant and neutral are much larger than negative or positive respectively. So we're not going to use those. We'll just use negatives and positives. So that means we're going to be looking at this kind of data, and we're only going to use the tweet text. We're not going to use the other features. I'm exploring. So I'm going to have tweets rows versus words as columns. So using a count vectorizer, this is what I get. It counts the number of appearances of a given word in a given document. Document 0 has all once and once, and so on and so forth. And we also use the term frequency inverse document frequency representation. Now, a point to make here, as we explore the data, there are a lot of tools and techniques out there, and we should be exploring the tools and techniques we might use. I can't present them all in a course. There's far too many. We need to have an attitude of exploration about the tools and techniques as well as exploring the data itself. For example, we can use a feature selection method called selectKBest based on a scoring function. So the F class if is using the F score that's related to analysis of variance and statistics, and mutual information classification uses mutual information for a discrete target. It calculates the mutual information and between a feature and the target. It does that for all the features, and then it gives you the best, however many K you want. Here we're using K equals 20. Here we're looking at K equals 50, and our features here are words, so we're getting word lists, and notice that they are slightly different. So why are they different? Which one should we use? Exploration. Here we have our test train split. We use a random forest classifier. Our best score is only about a 71, and our best estimator scored on the test data is a 0.719. And here are the 50 words used by this random forest. Notice that we have the words ice and cream and sandwich. We also have this ice cream sandwich all as one word, and we have ICS, that's probably ice cream sandwich. So the data we're looking at here was actually collected when Google announced their ice cream sandwich operating system for Android. So these may all be the same. Ice cream sandwich, it turns out that that phrase, ice cream sandwich, is either not in a tweet or the entire phrase is in a tweet 99% of the time. Notice also we have this HTTP. Why did it use that? Well, that was a pre-processing error on our part. We didn't handle URLs. I'm not sure what that means. Dozen, dawn, well, we probably cut it at a apostrophe T and lost the dozen and don't word usage. So, lematizer, a stemmer, a tokenizer. Uh, Not only are those questions, we also need to predict phrases. For example, ice cream sandwich instead of the words individually. And notice in some places, in some tweets, it did get compressed all together into one single long token word. So n-grams are n words in sequence. Ice cream sandwich is a 3-gram. But now the issue becomes speed. If I've got 1,000 words and I'm looking at trigrams, 3 grams, then that's a billion possible 3 grams. And working with a billion features means this problem is going to be high velocity. So because of high velocity, we often use alternatives to random forests. See, random forests are great, universal approximation, diagnostic trees, but compute times grow exponentially with the number of features. So we're going to get some alternatives, but first let's review Bayes' theorem. Remember, our joint probability density is defined in terms of conditional probability, as we see here. But notice that if we have the joint density is probability of A given B times probability of B, it's also the probability of B given A times probability of A, and we can take those and get Bayes' theorem. The probability of A given B or conditioned on B is equal to the probability of B conditioned on A times the probability of A divided by the probability of B. And remember, in what we're about to do, our goal here is faster, not better. Let's look at a Bayes classifier. We have feature variables x associated with a vector space V, our y associated with labels 0, 1, and that means that y conditioned on x is what's known as a Bernoulli distribution. We have trial data. We actually have values of small x's with the associated labels y's. Those are supervised data. And the variables that we use to represent these trials look like this. Bayes' classifier is a function from the vector space to the two-element set 0, 1, given by this definition. 0 is the probability that y is 1, given that x is xi is less than or equal to a half, and 1 if that probability is greater than a half. Notice this is one trial. The probability that y is 1, given that x is xi, that's called the regression function. And the way we measure errors is for any classifier h mapping the vector space to 0, 1, r of h is the probability that y is not the same as h of x. So Bayes' optimal classifier is actually a theorem. Let's remind ourselves of the regression function and our residual for measuring error. We use those to define excess risk. That's for a given classifier h, it's the residual or error for h minus the residual error for the Bayesian classifier f. And we can prove a theorem that the excess risk is non-negative, which means that the Bayesian classifier has the least error, the least residual. We call this the excess risk in using a given classifier h with respect to the Bayes classifier f. But notice this means that we must know exactly our regression function. And that means given any x sub I, we have to know exactly what the likelihood that y is equal to 1. That's equivalent to knowing the true model. So instead, let's look at our vector spaces Rn and our vector variable x in terms of the variables x1 to xn. And that means our regression function, probability y is 1 given that x is x, small x, can be written as the probability that y is 1 given that the variable x1 is equal to the outcome x1, so on, to xn is equal to little xn. So we often use data to estimate this regression function, probability y is 1, when the vector variable x is little x, which is written in this way. And notice that means that we're actually looking at the ith individual feature having the outcome little x sub I for I equals 1 to n. For example, the ith word in a text classifier. So Bayes' theorem looks like this, and you'll notice that I can suppress all the outcome information and just write the variables. That just cleans it up a little bit. And then we're going to assume conditional independence, that the probability of x sub I given y is the same as the probability of x sub I given y and all the other feature variables. What that means is that this probability of y given x1 to xn can be written instead as some constant c times the probability of y times the probability of x1 to xn given y. This is just Bayes' theorem because c here is the probability x1 up to xn. And notice we can get that c from the data, so we're not going to worry about it. It's just a constant. But our conditional independence means we can write this as a product. So using the product symbol notation, this is what my Bayes classifier, my naive Bayes classifier looks like. And because c is a constant and it's non-negative, it doesn't play a role in finding an argmax, which gives us our naive Bayes classifier. So given a vector x that's an observation of xi1 up to xn, then our y hat prediction is the argmax over the possible labels of y. Notice I'm using not just binary, but this is for any finite labels for y. It's the probability that y is c times that product of that we get from assuming conditional independence. So empirically, the probability y is c is just the relative frequency of c of the class. And the probability of xi, given that y is c, is the relative frequency of the ith factor having value xi over the subset of those trials that are actually in class C. So we get both of these quantities from the data, which means we can make predictions for a given unlabeled observation bold X. So in comparison, naive Bayes to a random forest, well, naive Bayes is not a universal function approximator, but a random forest is. And conditional independence is problematic. It's very important when working with text data that you determine phrases if you're going to use naive Bayes. Words in phrases are not independent. For example, the phrase New York means that the word new is dependent on the word York. And random forests are not fast. That's why we're using naive Bayes. Random forests can be very slow. Working with text is often computationally expensive. That's why we often prefer naive Bayes. That is, when we're doing text problems, compute time is very often a factor. And when compute time is a factor, our first pass tends to be for understanding. Our second pass is very often what's called a proof of principle. And both of these are often based on a much smaller representative sample of training data. So I encourage you to sample the data down, maybe using stratified k-folds and just using one fold. But get a smaller set so you can develop your model and you can test it thoroughly. Then you can extend to all of the data that you have. So 85% of data science projects fail because 85% of data scientists think some black box algorithm will do all the work for them, because 85% of data scientists do not use a problem-solving approach, because 85% of data scientists prefer working with less data, smaller data. Yes to all, but they're all aspects of the same problem. 85% of data scientists try to create solutions without first understanding the data. See, data science is information and feature engineering. That's what we do. Multi-pass problem solving where we build understanding and build and build and build. And feature engineering to incorporate that understanding into our models.